Hello everyone, this paper is 970211 October-November paper 2025. So the first question is, the table shows some physical quantities. Which row correctly identifies the quantities as scalars or vectors? So first you have to know what is a scalar quantity, and it's a quantity that has only magnitude, and vector quantity has both magnitude and direction. So the distance, speed, mass, time, these are scalar, and displacement, velocity are vector quantities, and there are some other vector quantities as well. So acceleration, since it is velocity divided by time and velocity is a vector quantity, this acceleration is a vector quantity, and charge is a scalar quantity. Kinetic energy, all type of energy, whether it is kinetic energy, potential energy, elastic energy, all type of energies are scalar quantities. And wavelength, since it is the distance between the two crests or 2 points on a wave, nearby points like the same points, the distance is always a scalar quantity. So the correct option is option D. Second question is, two quantities are measured. L is equal to 6.8 plus or minus 0.1 centimeter. So this is the quantity and this is the uncertainty of the quantity. And T is equal to 2.42 plus or minus 0.08 seconds. L and T are related to X by the equation shown. So X is equal to 4 pi square L divided by T square. What is the calculated value and uncertainty of X? So you can easily get the calculated value by just substituting the absolute values of L and T. So for finding calculated value, you just need to substitute. So it will be 4 pi square multiplied by the actual values of L, which is 6.8, divided by T square, so it's going to be 2.42 whole square, and the value of this is 45.8 centimeter second square. So this is per second square. This is what's the calculated value. So to find out the uncertainty of it, you're finding the you can use this formula. So quantity in a reading is an estimate of the difference between the reading and true value of the quantity being measured. So the uncertainty here, 0.1 and 0.08 are the the difference between the actual reading and the true value. So if the quantities are added or subtracted, then add absolute uncertainties, and if the quantities are multiplied or divided, then add the percentage uncertainties. Okay, so here they have multiplied and divided, right? So we'll find the percentage uncertainty of each. So percentage uncertainty of the value of L. So percentage uncertainty of L is gonna be that delta L divided by the actual value multiplied by 100. So if it is on the percentage, it's going to be multiplied by 100. Otherwise you can get by just dividing the value. So it's going to be 0.1 divided by 6.8, so multiplied by hundreds. So it's nearly equal to 1.47 percentage. So similarly, if the percentage uncertainty of the T value, it's going to be 0.08 divided by 2.42 multiplied by 100, so that's gonna be 3.31 percentage. So here you need to find out the total uncertainty. So 4 pi square doesn't have any uncertainty, but the percentage uncertainty of X will be equal to that whatever be the value of the L, so it's 1.47 plus the percentage uncertainties are added, right? So here there is two t values. So if you are adding it 2 times or multiplying by 2, is both are the same. So the percentage uncertainty is 8.09 percentage of it. So the percentage uncertainty is this much. So we can find out the absolute uncertainty of this value. So it's gonna be 8.09 percentage of the 45.8. So it's gonna be, you need to change into the fraction. So you are dividing by 100, so that you are getting the absolute value multiplied by 45.8. So that's equal to 3.7, nearly equal to 4. So the uncertainty is gonna be plus or minus 4. Alright. The uncertainty should be one significant figure and the value must be rounded to the same decimal place. So here it is of one decimal place, right? So you have to change this 45.8 to same decimal space. So here there is no decimal space. So the value is gonna be 46. That's why you are not taking this A and B, but instead this D, the option 46 plus or minus 4 will be the value. So it's because of the uncertainty doesn't have any decimal places. So the third question is, what are the SI base units of watt? So the SI base units are 7 and these are those values. So you need to find out for the watt. What is the unit of power? Unit of power is watt, which is represented by W, and power formula is the energy per time or work done per time. So you can split the work done into force times the distance divided by time. So here you can convert into the units. So the you can change the power value as the force is MA, so S divided by T. So you can get the unit of P as the mass is in kilograms and acceleration is in meter, s to the power of -2, and the distance is always in meter divided by the time is in seconds. So the when you are making it more simple, it would be kilogram meter square, and here s to the power of -2 and divided by s. So we have to move that denominator to the numerator, so it will be equal to s to the power of -3. So the option is B. So the next one, the diagram shows two forces 6 Newton acting on an object. The angle between the lines of action of two forces is 60 degree. So what is the magnitude of resultant force? So there are two basic methods to find out the resultant force. So the first one is triangular vector addition, triangular method, and the second one is the parallelogram method. So you can go for either of the method. So here if it is or otherwise, to find out the resultant, you can go for the law of cosines. Okay, that is also possible. That's also you can use. So the law of cosines can be used, and here the resultant will be the square of a square plus b square minus 2ab cos theta. This is the formula gonna be. So here I'm using the triangular law of vector addition. So you can make the perpendicular like here the 6 Newton is in horizontal. This 6 Newton is at an angle 60 degrees. So I can find out the components of it. One is perpendicular and another one is horizontal. So the perpendicular component would be 6 sine 60 and the horizontal component would be 6 cos 60. Okay, so if these two are acting in the horizontal and this one is acting in the vertical one, you can find out the resultant by using the Pythagorean theorem, Pythagoras theorem. So here the resultant will be equal to the square root of the two values. So two legs. So first one, if you're adding the horizontal one, so it's gonna be 6 plus 6 cos 60 whole square. Then you're adding the second leg, which is 6 sine 60 whole square. So by this also you can try. After the calculation, it's gonna be 10.39 Newton. So it's nearly equal to 10. So the option is C. So the next one is, a goods train passes through a station at a constant speed of 10 meter per second at a time t is equal to 0. An express train is at rest at the station. The express train leaves the station with a uniform acceleration of 0.5 meter per second square just as the goods train goes past. Both trains move in the same direction on straight parallel tracks, at which time t does the express train overtake the goods train. So the condition is like this. Goods train is having a constant speed and express train is accelerating. So here you need to find out the condition. So when it is overtaking, so the overtaking condition, when the express train can overtake the goods train, and that is when positions are equal. So they have to have a same positions. So you need to find out the positions of each. So if you are finding for the goods train, since it is moving with a constant speed, you can find out the distance of the goods train as distance is equal to velocity times t, and that's gonna be 10t. If you're finding for the express train, the let's represent it with SE. The conditions are that initially it is at rest, so initial velocity is 0 and the acceleration is 0.5. So you can choose the formula as ut plus half at square. So this component goes to 0 and the next one is half 0.5 t square. This is the formula. So we can substitute in the equation in the condition. So where the SG is equal to this SA, both distance are the same. So 10t is equal to 0. So here the value is 0.25 t square. So t and t get cancelled. So t is equal to 10 divided by 0.25 and that's gonna be 40 seconds. So the option is D. Then the question number 6. A ball is held above the ground and released. It falls to the ground and bounces several times. The graph shows the variation with time t of the velocity v of the ball. So this is the graph. 4 points on the graph are labeled P, Q, R and S. Which statement is not correct? So we'll check each of it. So the first one, the area under the line PQ represents the initial height of the ball. So actually the area under the velocity time graph will be representing the distance. So since it is falling from a particular height, so here is the ground and the ball is left from here. So initially it will be at a particular height, and as the distance is covered, the velocity will be increasing. This line is representing the height. So initially the velocity is 0, then as the distance moves, the velocity increases and reaches a maximum just before hitting the ground. So this is basically represents the height, so it's a correct statement. And the second one, the collisions of the ball with the ground is inelastic. So definitely it is, because each of the time the height is different, which means that the energy is low. So it means the second option is correct. So for the collision to be elastic, both the momentum and the kinetic energy should be the same. So here after each of the bounce, the velocity, maximum velocity decreases, which means that the kinetic energy is not the same. So it is an inelastic collision. Then the C option, the gradient of the line RS represents the acceleration due to free fall. So here RS is having the gradient. So it's the velocity time graph. For a velocity time graph, the gradient is representing the acceleration. So that is also a correct statement. Then the last option D, the maximum upward velocity of the ball is reached at point P. So this is the wrong one, because the maximum velocity is either on Q or at R, since it is so, because that's the maximum, so either in the positive side or the negative side. So maximum upward velocity will be at R, because over here is the O position, Q is at the ground. So when it reaches over here, the velocity will be on the downward direction, because it's moving downward direction. So at the maximum, it will be like when it goes to increase the speed, the velocity will be in the upward direction. That's represented by the R. So it's definitely not at P, because it's given the velocity is 0 at the point. Then question number 7, an object is projected horizontally. The object falls a vertical distance y and travels a horizontal distance x before landing the ground. A second object is projected horizontally with the same initial velocity and falls a vertical distance 4y before landing on the ground. Assume that air resistance is negligible. Which horizontal distance does the second object travel? So here let's consider the object. So it's having a vertical distance and a horizontal distance, means the object is having an initial velocity which is like horizontal, and for the vertical motion it starts from the rest. So at this point there is a initial velocity, and that's the same for both. In the vertical one, only acceleration is what happens. So let's consider the vertical motion of both the object. So we are considering for the first object, it will be the distance, vertical distance. Let's represent it with y. So y is equal to ut plus half at squared is the formula, but since the initial velocity is 0 in the vertical motion, not in the horizontal one, only in the vertical one, the initial velocity will be 0, because it's given that horizontally with the same initial velocity, not a vertical one. So the formula goes like y is equal to half. Of course, the acceleration would be acceleration due to gravity, t square. So let's consider the time taken for the first object to be t1. This is the formula for the distance. So after rearranging, you will get t1 is equal to root of 2y divided by g. So let's consider the second object. So second object is also following the same formula, y is equal to half at square, but here the vertical distance is gonna be 4y and the acceleration is g, and the time, let's represent it with 2. So by rearranging, you are getting this t2 is equal to root of 8y divided by g. So here you can split the 8 as 2 times 4. y divided by g means you can take this root 4 outside, which is gonna be 2. So leaving inside 2y divided by g. And what is 2y divided by g? That is the time taken for the first object. So t1 is equal to 2 times the, t2 is equal to 2 times t1. So the time taken for the second object is double the time taken for the first object. So let's consider the horizontal distance. So we are considering the horizontal motion now. So it's given for the horizontal motion, there is a initial velocity value. So you can find out the distance, which is represented by x. That is gonna be velocity times t. So velocity, let's take it as v, and the time is t. So for the first one, it's gonna be v x1 v t1. But for the second object, it's gonna be x2 is equal to v t2, and the v stays the same because it's given. So here you can just substitute for this t2, like v is equal t2 is equal to 2 t1. So it's 2 v t1, and what is the 2 here, v t1 here, the distance by the x, right? So for the first object, so it's 2 times the x. So the correct option is option B. Next question, question number 8. A sphere forced from rest through air. The graph shows the variation with time of the sphere's velocity. This is the graph. Which diagram shows the forces acting on the sphere when it is at the velocity corresponding to point P on the graph? So here, when it is falling downward direction, the weight will be acting downward, and the upward force will be of the air resistance, so force A. So since over here it's not a horizontal one, it's having an acceleration. Okay, so, because the if the at this point, if the gradient is 0, then we can find out the acceleration is 0. But here at the point P, there is an acceleration, there is a gradient, so there is an acceleration. So the resultant force is gonna be ma, and it's mostly here it's not balanced by the air resistance, so the weight will be the higher one, and minus the force due to the air resistance. So here, since the acceleration is keep on lowering, it's not much as before, it's becomes less. So this acceleration must be less, but the weight should be higher than the air resistance. So the air resistance will increase as the speed increases. So at one point, both of them will become equal. Then at the point, there is no acceleration. That's the option given here. This is completely wrong, and the B option, there is no for air resistance, that is never gonna be happening. And this one, weight is greater than the air resistance, so the correct option is option C. Question number 9. In which situation is the total linear momentum always conserved? So this is the principle of conservation of momentum. For a closed system, the total momentum before an interaction is equal to the total momentum after the interaction, which means that it should be obeying a closed system. So in the first one, it's in all the collisions between two objects. No, definitely not, because it should be having a isolated system. So that's why the option C is the correct one. So in the remaining options, it's not showing the closed system. Question number 10. An object of mass m moving with velocity 9 meter per second has a head-on elastic collision with a stationary object of mass 2m. After the collision, both objects are moving. No external forces act on the system. What is the velocity of the object of mass 2m after the collision? So here you are considering the momentum conservation, but before that you have to find out about the condition of elastic collision, because here it is given it's an elastic collision. In the elastic collision condition, there is an elastic collision condition, and that is the relative speed of approach is equal to the relative speed of separation. So when they are approaching, the relative speed is 9 minus 0, because the object M is moving with the velocity 9, but the second object is stationary. Then it is equal to the relative speed of the separation. So they are, since one is heavy one, the stationary one is heavy one, definitely. They are both are moving, but it must be in the opposite direction, so we can assume like this. So 9 is equal to v2 minus v1, or you can write down v1 is equal to v2 minus 9. So now let's consider the momentum conservation condition here, because it's a collision. Definitely the momentum should be conserved. So initially the two masses, so first one is m, second one is 2m. So m is moving with velocity 9, here the object is stationary, and after the collision this m is moving on one side and 2m is moving on the other side. So here this one is moving with v1 velocity, the second object is moving with v2 velocity. So here momentum before collision, momentum is only for the object m, should be equal to the momentum after collision. So momentum before collision will be m 9 mass times the velocity is equal to momentum after collision. Both of the masses has the momentum. So m v1 for the first object and 2m v2 for the second object. So here you can just cancel this m. So m gets cancelled over here, and 9 is equal to v1 plus 2v2. Substitute this v1 over here, that gives you v2 minus 9 plus 2v2. So here once you open the bracket, it's v2 plus 2v2, so that gives you 3v2 minus 9. So here the 9 and 9 has put together gives you 18, and the v2 will be equal to 18 by 3, and that's gonna be 6. So the speed is gonna be positive 6 because it moves on the right side. So the option is D.